very much. Good morning, everybody. So thanks a lot to the organizers for organizing this beautiful workshop here in Trieste and for the invitation to speak. So I'm going to tell you about this recent work in collaboration with my postdocs here at CISA, Panos Charalambous and Shreyas Agrawal. And it's going to be about some sort of correspondence or relationship between two important null hypersurfaces in asymptotically flat spacetimes, which are null infinity and the horizon of a black hole. And in particular, I'm going to discuss this relationship in general ground, and then I'm going to use this to show that it implies an infinite amount of conservation laws at the black hole horizon and at null infinity, and that in fact that these two conserved quantities, these two sets of conserved quantity can be exactly mapped to each other. So the plan is as follows. So I'm going to give you some motivation, broader context for why I'm interested in this. Then I'm going to describe this and contrast these two geometry, which are black hole horizons and null infinity, and explain how we can actually relate these two things together. And then I'm going to turn to the matching of conserved quantity when it comes to perturbation, gravitational perturbations of extreme rational nostrums and generalization of it. So I'm very happy to take questions or comments during the talk and to be interrupted as much as possible. But let me start with motivations. And if I start to write too small, let me know. So the general context of this work has to do with trying to better understand gravity or quantum gravity in 4 space-time dimension asymptotically flat spacetimes. With the idea of have a better understanding of quantum properties, well, properties of realistic black holes, like the one we see in the sky. And when it comes to understanding quantum gravity and quantum properties of black holes, I think it's fair to say that everything we have understood about this question is closely connected to the recent and beautiful successes of ADS-CFT correspondence. However, this correspondence applies for a negative cosmological constant, and if we want to understand if there is such a thing of a holographic correspondence in asymptotic flat spacetime for which we're going to take on the equal 0, of course, the Sitter holographies, it would be an even better setup, but it's not the one I'm going to discuss today. Then the question is, can we come up with the holographic correspondence for asymptotically flat spacetime to address this question of more realistic setups, such as astrophysical black holes. So can we understand flat space holography? So this is not, of course, a new idea or a new topic. As early as the late 90s, people have attempted to address this question. However, it turns out to be much harder to formulate than in ADS-CFT for a bunch of reasons, conceptual reasons, and technical reasons as well, but mostly this has to do with the fact that the conformal boundary of flat space is much more complicated than the one in ADS, and this triggers new challenges for holography. But in recent years, there have been a recent progress in flat holography. realization that somehow the infrared structure of the asymptotic structure of flat spacetime was very rich. And then there are some infinite dimensional symmetries that act at the conformal boundary of asymptotically flat spacetime. So here is the Penrose diagram of asymptotically flat spacetime. And we have the boundary of this diagram, we have the future null hypersurface, which is denoted by this calligraphic letter scribe, of the future null infinity. And we have a past null infinity as well. And the key new input, so to say, into flat space holography was the realization that on this conformal boundary, there are some infinite dimensional groups acting. So I have in mind the works led by Strominger, started by Strominger and collaborators somehow 10 years ago until now. Okay, there are many people involved, of course, in this program. And out of these symmetries, there are the so-called Bondi, Messner-Zach symmetries, which are the asymptotic symmetries of flat spacetime. And the key point is that they act both at the future and at the past simultaneously. So, in other words, these are global. Well, this symmetry leads to global, meaning not only in this future or in the past, but in the entire space-time. Also, by the way, time-lag infinity, where massive particles go to, and a past time-lag infinity as well, but I'm not going to discuss all of this. So, the presence of this infinite dimensional symmetry provide an infinite set of conservation laws for any, say, scattering processes happening in flat space. And these conservation laws, of course, give very strong constraints for the S matrix, gravitational S matrix, for the BMS symmetries, but in general for the putative dual theory of quantum gravity in asymptotic flat spacetime. Okay, so this is essentially this is the starting point of what I want to talk about. Is there any question about that? I'm not assuming everyone is familiar with this story, so if you have any question. But essentially, this BMS symmetry, they are the analog of what are the conformal symmetries for the SCFT. Okay, they play the same role, except that there is an enhancement, so they are more like the 2D CFT symmetries because they are infinite dimensional, and there's some analogs and gauge theories and so on. And the idea is that they are new constraint, but again, the global, so they were known since the 60s, the fact that they are these symmetries in close to a null hypersurface, but the key input of Strominger and others is that they are global, okay? That's what I want to emphasize. So this is needed actually if you want to understand how this constrain the S matrix, for instance.
Can they be understood in some flat limit? Yes.
Okay, so it's a very interesting question. So turns out that these BMS symmetries, in 3D, you can very cleanly obtain them from 2 copies of Virasoro from ADS, and then redefine your generators and take the flat space limit, you get the BMS3 group. In higher dimension, it's not the case. if you want to see them from a flat limit of the asymptotic symmetries of ADS, then you would need to do something we usually never do in ADS, which is not to impose Dirichlet boundary condition. You need to allow what people call leaky boundary condition, when you allow your field to leak out through the boundary and not to bounce back on the. So if you do that, you have not really a group. You have a algebroid, whatever. It's more complicated stuff, and then you can see the BMS arising from this enhanced group. But yeah.
Do the boundary condition that you mentioned in ADS correspond to imposing the boundary condition at the continuation of the de Sitter horizon, or something different?
The de Sitter.
Like, I mean, if you're in ADS, you have also like, I mean, you have somewhere in the complex plane the analytic continuation of the DS horizon.
So you mean the time-like boundary of the space-like boundary of de Sitter? Like you want to see that also from de Sitter. Yeah. Mm-hmm.
Yes, what then?
So no, I don't think people have looked at this from the analytic continuation of the Sitter horizon. But anyway, it's not. You see, they don't form a group. It's a more complicated structure, so it's a tricky deal. So the short answer is not really, except in lower dimensions. Okay. So very good. So it was about these asymptotic symmetries, but and okay, there has been a lot of work along those lines. I'm probably going to keep that.
Is it the point that these symmetries are supposed to give you dynamical information as well, or it just
Yeah. So the idea would be that they would also constrain a dynamical process, but I think that so far most of the advances in flat space holography has been at the level of kinematics, namely recasting some correlation, some S-matrix into some boundary correlators having symmetries. Yeah. But there are some interesting questions. What are the fate of the symmetries at the level of dynamics? Okay, there are many. I think I could say that. Okay. So now the question I want to ask is, since the symmetry were so important in this, even formulating these new candidates for flat space holography, so far, celestial, if you heard about celestial holography, has not been dealing at all with the presence of black holes so much. So the question I'm interested in is, what happens now is if you have a black hole in the space-time, which have their future and past horizon, what happens to these conservation laws? Are they modified, and what form do they have? I don't have the full answer to that, but this is the direction in which I'm trying to go here. So what happens? There is a black hole, which is asymptotically flat. Then we expect new contributions. Horizon. And the question is what happens to the conservation laws. So, and this is where this work takes root, because in the same way that, as I emphasized, you need to understand how to match or relate or glue together these two boundary future and past infinities. I want now to understand how to relate the horizon with infinity together. What happens to the symmetries? Turns out you have also very rich symmetries near the black hole horizon, and how these things talk to each other. So you need somehow to interpolate or relate horizon and turn past non-infinity. And this is what I'm going to discuss next. Is there any other questions or comments? Let me know. Okay. Good. So, to do that, to discuss this, I need to first remind you or explain a bit what are these geometries near this conformal boundary and near the black hole horizon. So I will start with the geometry of non-infinity. Right. Okay, so this brings us back to the 60s, as I said. I'm going to use these coordinates where u is a retarding time running along this non-hypersurface. You have a radial coordinate r, which if you take r very large and you fixed, then you reach this boundary, and then you have also this. So each point here is a sphere. You have these transverse coordinates. I'm working in 4 dimensions here. And I'm going to discuss the notion of asymptotically flat spacetime. So this is back to the work of Bondi, Penrose, Troutman, all the people in GR at that time who made this seminal works on this. And they came up with a good notion of what it means to be flat seen from a very far distance. So what is the notion of asymptotic flat spacetime? So we are going to, well, essentially, it's a metric which is flat plus 1 over r correction. R is taken to be very large, keeping the other coordinates fixed. Okay, so you do a large r expansion, and in these retarded Bondi coordinates, you can always write your metric in this form. I will manage to write everything here. So this is just a gauge choice at this stage. So now what matters is to explain you what are these powers of R here. So what are the appropriate fall-off conditions for the metric. And this expansion involves some functions. I'm going to explain a bit what they are. So the dot means, of course, terms that are subleading in this 1 over R expansion. And this is dictated by, the form I'm writing is not arbitrary, it's dictated by some well-thought fall-off condition. If you're familiar with the notion of Penrose compactification or asymptotic in simple spacetimes, plus Einstein's equations, which dictate the form of this expansion. So essentially the first thing to notice is that the leading term of this expansion give you back exactly Minkowski, so just flat space, because this is just the S2 metric, so the Wronskian metric. So it's just Minkowski space written in this coordinates. Okay, so just one, and this is just R squared times the S here on the metric. Matrix here. And then you have these corrections which involve these quantities here, which depend on mu and the angles. So this object here in the expansion is called the boundary mass aspect. Essentially, it captures the energy of your isolated system you're describing. This is the angular momentum aspect. So essentially, if you take, for instance, a curved black hole, you write it in these coordinates, this boundary mass aspect will just be a constant, then it will be just the mass of the curved black hole. And if you integrate this NA guy over the sphere, then you will get the angular momentum of the curved metric. Okay? And all the rest would be zero. Okay, so it's essentially the energy and angular momentum. And here you have what is called the gravitational shear. Which encodes the two polarization tensor of your graviton. And in particular, this quantity, which is the time derivative of CAB, if this quantity here is non-zero, then it means that you're describing a system which is emitting gravitational wave. Okay, so for this reason, this thing is called the Null tensor. Okay, so this captures your outgoing radiation at null infinity. So you really have to imagine that you have here, so say, a binary black hole merger in the center of the space-time. You're very, very far away here at LIGO with your detector. The merger is emitting some gravitational radiation and is reaching null infinity. And the quantity, the gravitational wave, is measured by this quantity. In fact, there is a famous formula that Donnay derived, which is exactly telling you how much the energy of the system decreases in time, because there is a minus here, due to the emission of gravitational wave. Okay? It's the Bondi massless formula, and you have to imagine that in the 60s, these guys no one was convinced that gravitational wave existed, and Bondi and this kind of formula was sort of very first proof, so to say, of convincing people that gravitational waves were real. Okay, so it was important in the history of GR. Is there any question about? That's all I'm going to say about the geometry of non-infinity. Of course, there are many subtleties and things that I'm not discussing, but is it clear more or less? Okay. Then, yeah, the relationship with these BMS symmetries I was talking before, yeah, is that if you look at the symmetry preserving this expansion, then you find the BMS is equal to BMS coded.
If the black hole is just static there, isolated, is the is 0, right?
Yeah. Yes. There is no, well, for, yeah. Even this quantity would be 0. Okay. So now I'm going to do a similar thing near a black hole and do a similar expansion. Of course, now near the horizon. So this will give me. I'm going to call a near horizon geometry. So now we forget about what happens very far away, and we are instead interested in what happened close to the black hole horizon. So in this case, also I'm not hypersurface, but it's more convenient to use an advanced time v. So it's a future horizon, and I'm also going to use some radial coordinates. Now I'm going to call rho, and I'm going to set it so that my horizon is at rho equals 0. Coordinate system. Yes, and I'm going to use V0 and again some angular coordinates. So you have this rho equal constant line, sometimes people call it the stretch horizon. So I'm doing now an expansion near rho equals 0. Let's see how to organize the blackboard. Will give me a near horizon metric. And again, I have some expansion with some functions here appearing. On purpose, I'm writing in a sort of gauge which is well adapted to compare with the one at Scry. And then have this last line. So of course here I'm writing everything. I have picked a specific gauge and coordinate system. There are ways which are much more invariant of talking about this geometry, but for sake of concreteness, I'm using explicit coordinates here. And now we have this in this near this rho equals 0 expansion. We have these objects here, which depend on the advanced time and the angle. So this thing is called kappa because, okay, if your horizon is killing, this kappa will be the surface gravity of your horizon. But this expansion is much more generic than it's for any black hole. As long as it has some smoothness condition, the horizon is smooth enough, you can always write down this expansion. Some mathematicians have proven this. Page 16. Okay, this guy here is often called the twist or the Ajicek. One form, it has many names in the literature, but essentially you can imagine it is related to the spin of your black hole. And then this is the horizon metric. Plus some corrections. And in particular, this omega AB gives rise to two important quantities that I want to briefly discuss. So, if you consider the time derivative of this object, omega AB, of the horizon metric, then you can take its trace, and this gives you the expansion, scalar expansion of the horizon. So literally how your horizon increases or decreases as time goes. And the traceless part of this is, okay, we're not going to care so much about that for the purpose of this talk. It's called the longitudinal shear. Okay, so how essentially your horizon gets deformed. Okay, how your sphere gets deformed. So, is there any question on that? I'm just giving you a generic form of near horizon geometry. And of course, this is just the geometry. Now you have also to talk about the dynamics of this object. And it's okay, Einstein's equation, here are many equations. Let me just briefly comment on maybe the most famous equation, which is how this scalar expansion evolves in time. This is the Null-Rachel-Dury equation. Which plays a key role in Hawking's proof of singularity theorem, essentially. Comes from this equation plus some energy condition imposed. And then, of course, you have many more equations that I'm not writing here for how this quantity evolves. Okay. Good. So as you see, I mean, this is this is of course a much less. Okay, there are some. One can have some discussion about, you know, why this precisely powers of rho here. What are the assumptions? What not here? So it's on the less. Let's say that the same discussion can apply near null infinity. But okay, I mean, I think we are collectively gathering a good notion of what are the good boundary conditions near the horizon. Of course, this is subject to which question you want to answer and what kind of crazy scenarios you are ready to deal with. These are very conservative ones. And okay, now the question I want to address is, okay, as you see, these look very similar. I mean, of course, they are both null hypersurfaces, scry and the horizon, and you might wonder what is the relationship between these two things. And there is a nice way of formulating this. So I think I will have to, maybe I can remove this. Scry and the horizon. And the geometric statement to which extent scry can be seen as a horizon is the following, is that scry can be seen as a particular type of horizon, which is extremal expanding horizon for the conformally completed spacetime. Which often people call again physical metric ds tilde, which is conformal factor times the physical metric ds squared in my notation. This is just a conformal factor with some scale divided by r. So that's the statement that essentially can that we explore and make precise. There are some, I mean, in the work of Ashtekar and others, there are these ideas were already present, but somehow there are many layers to this that we learn better. So there are many ways of, you know, if you're a conformal geometer, this is might be obvious. But in the way I'm presenting things, a very concrete way of understanding the statement is the following. So you start with your near, the expansion of metric near null infinity. When you finish on null infinity, you do conformal rescaling. This gives you the physical metric. And then if you do that, then you can see that your near scry expansion will match exactly with an expansion of this form, like a near horizon expansion. But a particular one if you want this fall-off condition or near horizon expression to be satisfied, then it will set some of these components to 0. So basically what you're going to find is that kappa must be 0. It also should be non-twisting. But this notion is less invariant. But I'm going to swipe some stuff under the rug, but also not non-expanding. So the expansion, you see scry as a horizon in the physical space-time, then it should be an extreme and a non-expanding horizon. So you can just, check that your near scry expansion is going to be mapped to a near horizon expansion with this specific value. Okay, I should stress that this is not, of course, a global statement, because it doesn't mean that, each time you have an asymptotic space-time, you have a horizon inside, right? So the map is, remember that the map relates different metric, physical and non-physical metrics, so it's not a global statement, but still it's a nice geometric picture of relating these two null hydral surfaces.
Sorry.
Yes?
Can I understand this statement? For example, if I think about the sitter, I have like the cosmological, I have this like this. I have the cosmological horizon and the point r equal to infinity, and I'm kind of colliding those two in the same fashion as I would be colliding to.
So you want to see this is the horizon, the cosmological horizon is sitter?
Yes, and am I not colliding that to actual r equal to infinity in the usual coordinates?
R equal infinity, which in your coordinate would be this boundary.
But I should get null infinity afterwards.
Ah, wait, okay. When we say R equal infinity, we have to watch out because what is called fixed is you take R infinity and you keep a null coordinate fixed, you end up at a null hypersurface, but you also end up at time-like boundary. but what you were saying is that, say again, I'm sorry.
I'm not sure. I'm thinking like if I write the sitter, I don't remember the name of the coordinate, but if I write the sitter metric.
Yeah, the quantary patch.
Yeah, writing this like the redshift factor f of r is like 1 minus r squared, something like that. Then when I send the sitter like scale to infinity, I just get 1, which is Minkowski.
Okay.
And then kind of colliding the horizon with r equal to infinity. So
Yeah, you have to watch out whether you are calling this with this or actually with the null hypersurface when you do that. So one has to be careful about.
So I think that this is what would be what happens if you look at the singularity. So there is some weird equation. This would be what happens. You have these two singularities that merge, and they precisely like the resulting structure is the structure on extremal horizon because you have the merging on these 2 points.
Okay.
I was wondering if this is like related to what you were saying.
Okay. Yeah. If it's you see if it match, it's just this is a conformal conformation. It just maps null hypersurface to null hypersurfaces. So it's maybe what happens. Maybe it's a version of that. We should talk about it in more detail. Okay. So yeah, in fact, yeah, this horizon could be a cosmological horizon. There is no, again, it's a very local statement here that I'm just doing some local expansions, and what matters at the end of the day is of course how this is matched to a global statement. So this is not so. What you see is that just you do an inversion, and then you have your near horizon expansion matched to a near square expansion. You can check it explicitly by doing this conformal inversion. So in general, this I call this a duality. I mean, this is probably too much, but. It's you know, there is to square you can always associate it a horizon, but the question of whether this horizon is an actual black hole horizon in general will not be the case, but there is an exception to that. So there is a particular case of this statement where it actually implies, you know, globally a very rich conformal isometry. Which somehow explains what is known as the Couch and Torrance symmetry. That arise for particular extremal black hole, which is extremal Armstrong. So the symmetry has been found somehow surprisingly by Couch and Torres in the 80s. And let me explain you what this is about. But the upshot is that you can. I mean, this is not an accident. It's actually how I understand the symmetry is a consequence of this more generic duality. Because it turns out that ERN is precisely a black hole, which is the extremal and non-twisting as well. So let me explain you the symmetry, and then I'm going to use this to talk about infinite set of conservation laws of ERN. So write down that metric. An extreme, Fresnel Armstrong, black hole. So the charge. I'm not writing the gauge field here, but the charge is exactly equal to the mass. So the discriminant then becomes a perfect square. Okay, which is the metric of ERN, and the horizon is located at R equal M. And this isometry is the following. So if you map this R to an R tilde, which is essentially an inversion. Then the metric of the ERN geometry so ds tilde is ERN black hole with R tilde instead of R. So when you do this, you perform this CT inversion. That's essentially, you find a conformal, it's an exact conformal symmetry of extreme Reisner Nordstrom, which is not so well known. It in fact can be written in a much more convenient way in using the tortoise coordinate. So I'm not going to write down the explicit form of the tortoise coordinates. But in terms of tortoise coordinates, just a reflection. Okay, so R star is sent to minus R star. And what it does is that it sends R equal M to R equal infinity. So it's exactly exchanging the future horizon, future null infinity, and the past horizon with past infinity. And what is fixed, so the fixed point of this inversion, conformal is the location of the photon sphere, which is at R equal to 1 for the platform. So, fixed point. So people who originally found this, they were surprised by this fact. But now I think it has been studied much more. In fact, there was a poster close to the coffee room about a student of Massimo Bianchi. So Massimo Bianchi and collaborators have explored some physical consequences of this Couch-Torrance inversion for deep brains and so on. And what I'm going to talk next is also some physical implication of the existence of this exact conformal isometry for this black hole. Is it clear? Yeah. So it's a pretty nice and peculiar feature. Now I'm going to. We started. Okay, so I'm trying to compute because we started late and my watch has a time delay, so it's not working properly.
It's 10 minutes.
Okay. So now I'm going to exploit this story, generic story I've been telling you about. Too much. An infinite set of conserved quantities and actually find new conservation laws associated with any spin perturbation around an ERN black hole. So I'm going to be in the same setup at Pablo's talk previously. So I'm going to essentially use the Newman-Penrose formalism for this and essentially work out Tucholsky's equation in this setup. So I'm going to do this for generic spin weight as perturbation ERN on ERN background. So I'm going to denote collectively this by psi s, when s equals 0, this will be some scalar perturbation. It's also going to encode for s equal plus or minus 1 electromagnetic perturbations together with gravitational perturbation. So as you've seen in the previous talk, these are encoded into these Weil scalar, psi4 and psi0, okay, which correspond to outgoing gravitation and incoming gravitational perturbation. But actually, our analysis unifies all these spin weights, and you can do it for any spin weight. But in particular, you can specify for those if you're interested. And so what we have to do, so I'm going to use this magic inversion, conformal inversion for this ERN geometry. So the goal is, well, what we have to do is essentially work out this Topolsky equation. And we are going to write them in this coordinate system, which is well adapted for some perturbation near infinity. So this is valid for any s. Let's see if I put everything here. It's not that long because it's a very simple geometry. So this Topolsky equation collapse to. Okay, I'm using at as bar. This is just the Laplacian of the two spheres. Doesn't really matter. 2s plus 1 are u acting on psi s. Okay. So these are the equations in using this well-adapted system of coordinate near scribe. Well, now I need to do some sort of expansion. I'm going to expand this psi now in near scribe mode. Okay, and these guys, as in the previous talk, I'm going to expand those in spin weighted spherical harmonics. Okay, so these are the spin weighted spherical harmonics. In fact, it's very easier than the spheroidal harmonics that we saw in the previous talks. Now I'm going to plug this into this master equation and extract some recursive relations for this quantity. So these are the near scribe modes expanded in spin weighted spherical harmonic for any spin weight. And I'm going to show you that from this equation you can extract an infinite tower of conserved quantities. So it implies you get the Gurdon relations as follows. For this psi SLM. And part of the work is to write this down in the right form so that you can extract these conserved quantities easily. So it's a bit lengthy, but it's not that bad. Okay. And from this, because it has been written in a very transparent way, you can see that immediately that if you set n equal s plus n, you have du of something equals 0, and so you get these quantities that are exactly conserved. It's a particular combination of this psi. I don't write as fast as Carlo, but I'm trying my best. Psi SLM. So this particular combination provides you with an infinite set of conserved quantity near infinity. But of course, as everything that has to be with gravity near square, Penrose has worked everything before, so these are nothing but the so-called Newman and Penrose conserved quantities that you might be familiar with. Okay? For any spin way particularized to this setup, but you can, okay. In spirit, these are the Newman-Penrose conserved quantity. You have an infinite hour of that. What is remarkable is that these are about linear perturbation, but at non-linear perturbation, you have 10 of those for gravitational perturbation, for instance, that remain exactly conserved. And as far as I'm aware, no one understands where this conserved quantity comes from. So they are largely remain mystery. For instance, we don't know if they can, when you have conserved quantity, we like to think that these are not a charge associated with some symmetry. These Newman-Penrose are not associated to any symmetry. So we don't understand, I think it's a bit of a shameful thing for us in gravity that we don't understand better where this comes from. But since I'm running out of time, what I'm going to tell you next is that, of course, you can do something similar now near the horizon. So essentially, you do same derivation. Well, okay, things changes, but you can run the same thing. And then near the horizon, you also find an infinite hours of conserved quantity. And here, some of them have not been written down before this work. And these are the conserved. So these, I like to call them A now. You can check the papers if you're interested in the explicit. This is a very analog kind of combo of these near horizon modes. I'm sparing you the details here. The key point is that, again, you have an infinite amount of them that are exactly conserved in advanced time. And for s equals 0, so for s equals 0, these are the so-called Aretakis charges. So these Aretakis charges were found in the mathematical GR literature by Aretakis, who was studying the, in this field, people have studied extensively whether or not black holes are stable, stability of black holes. And what Aretakis showed is that essentially an extreme rational nostrum is unstable against scalar perturbations. And in his proof, in his paper, along the way, actually his derivation relied on the fact that he exhibited an infinite amount of conserved quantities. He was looking at this setup, which are called Aretakis conserved quantities, and it's a very rich story. So these are key in the proof of linear instability of ERN black hole. So essentially, these quantities that have not written down, but we wrote in the paper, are any spin-weighted generalization for gravitational perturbation, electromagnetic perturbations of these Aretakis charges. So you have a very rich amount of conservation laws near the horizon, and still now the two things don't talk to each other. But of course, the upshot is that you can actually match these conservation laws. Is there any question about, I'm going to finish very soon, I promise. Let me know if there is any question about the status of these conservation laws.
Just a small
Yes?
one. You said that it wasn't known what symmetries they correspond to.
Uh-huh.
In this s equals 0 case as well, or maybe is there some improved
No, yeah,
understanding?
the same story. So the existence of these conserved quantities are also as mysterious as Newman-Penrose. So now I'm going to tell you that actually they are in one-to-one relationship between them. So, but you explain some mysterious conservation law with other mysterious conservation laws. So no one, maybe someone has a better understanding of that. Yes?
Yeah, is this related at all to gravitational multiple moments? So there's a paper by Geoffrey Compare where they show that multiple moments can arise as another charges of residual gauge freedom. So maybe could this be related to that?
Yeah, I think if it has to do with something is with multiples. In fact, in the paper of Vanderberg, the guy who is omitted in this BMS acronym anyway, he showed that for a specific setup, some of the Newman-Penrose conserved quantities are some specific combination of some multiple moments. And there's a very specific combination, like have 4/3, something very specific, but I think it's going under this direction. But why this specific combination? In fact, we'll have a IFPU a focus week on this topic, trying to hopefully
Before you
shed light on
erase,
that.
maybe can you solve the recursion when L is equal to n? L is equal to s plus n.
You want to solve?
Because now you just have a recursion for du psi.
Yeah, which when L equal s plus n is 0. You have du of something which is 0.
No, okay, but du psi is not 0. No?
Okay.
I mean du
Uh-huh,
psi.
uh-huh.
Let's say s is equal to 0.
Okay.
So you have a recursion for the function du psi n m n.
Yeah.
So can you solve this recursion? Is it possible?
Maybe, yeah. We haven't tried, but maybe, yeah. Well, in principle, you see in this setup, I think in this setup of ERN, we should be able to solve everything because of this, well, we should be able, because there is this matching between this psi and this near horizon, so I think it's a setup where actually, because of this magic conformal isometry, we can do actually a lot and derive some global statements. I'm going to just wrap up, but what we did is, aside from deriving these new towers for generalized spin wave perturbation, is to match these conservation laws one by one using this CT inversion couch and Torrance symmetry, which, okay, once you know it's there, it has to be the case, but it's actually a tricky thing to do it for gravitational perturbation because gravity is not conformal invariant, so you have to work out this so that will work. But the end result is that you have a one-to-one match between these Aretakis charges and the Newman-Penrose charges for any spin weights. So the one-to-one correspondence. So you have an infinite tower on the one side that corresponds to an infinite tower of conserved quantities. I should mention that we are not the first one to have looked at the story of matching Aretakis and Newman-Penrose. There's Bison, Friedrich, Lucetti, Real, Murata, and others a couple of years ago, but for lower spin weights. Okay, so this is a consequence of this inversion that I was telling you about. So I think I'm going to stop. Sorry for going over, and just mention some future maybe some conclusion and future directions. So we explored sort of geometry, what I like to call geometric duality, exchanging these null hypersurfaces, the horizon and scry, and this is the reason for there is, if you wish, a self-dual example. So it has nothing to do with self-duality in many other meanings. So the self-duality in the sense example is the ERN geometry, where this duality becomes an exact conformal isometry of the space-time, which is the so-called couch inference. We derive these conservation laws and match them one-to-one with Aretakis. Now you can wonder, what about beyond this very specific case of extreme rational Nordstrom? Actually, for extreme Ferrer-Newman, you don't have such a thing as an exact conformal isometry at the level of geometry, but there is a remnant of this geometry at the level of perturbations. So at the level of a scale or any spin wave perturbations. And we could actually do a similar computation for extreme Kerr-Newman, even though there is not this seat inversion. So it was useful. It's nothing we would not have tried if we didn't know about that. So we managed to do that for axisymmetric perturbation, but of any spin weights. I'm not going to write down the details. And maybe I can mention some future questions that I'm interested in. So I want to understand better whether there is some first principle understanding of these Newman-Penrose or Aretakis charges, maybe with the multiples. maybe it would be nice also to work out whether there are some implications for black hole stability theorems. Since these Arezakis conserved quantities were instrumental in showing the instability of ERN. And then it would be also nice to make contact with maybe, there was some paper make contact with the vanishing of long numbers and seat inversions. The story of horizon waveforms that Carl talked about last week. And of course, try to go away from extremality. And we have a sort of conformal inversions for non-extremal black holes. And it's something that we studied recently with the Panos Charalambous and Alex Luxaska a few months ago. So for this, the viewpoint of the photon sphere is very interesting. And it might be a way to get such a thing from non-extremal black holes. And I have more speculative stuff going to do with shadow operator and celestial CT, but I'm going to stop here. Thanks a lot for listening.
Any questions? Okay, that's cool. So you mentioned the nether currents, but nether currents I guess are useful because you can evaluate them at different points. So isn't this what you work on there? With somebody on Skype, not on the horizon?
Yeah,
Them.
yeah, absolutely. But what we don't have is an understanding of how these conserved quantities are really neutral charge. Say that there are some neutral charge associated to some symmetry, and this is the reason for the existence of these conservation laws. That's what I meant. Yeah. So this is not understood.
They don't have to do.
They don't have to. It's just that usually they are. Yeah. If someone knows a similar setup where they don't, would be very happy to. But all the charges I know in gravity, they are neutral charges. These are some counterexamples of that. Yeah. Maybe there is some hidden symmetry.
Any other questions? If not, let's thank our audience.